Our current topic is we're going to take a look at the rates of chemical reactions, starting with our lab exercise, the clock reaction, which will examine what influences the rate or how fast a chemical reaction will proceed. A rate is always something measured per unit time. For example, miles per hour is a rate. Hot dogs consumed per second would be a rate at one of those hot dog eating contests. In chemistry, the rate is measured in moles per liter per time. Given that moles per liter is concentration, for a chemical reaction, our rate will be measured in terms of the change in concentration per unit time. This will be the unit of measure for the rate of a chemical reaction. There's several things that can influence the rate of a chemical reaction. A short list of things that can influence the rate of a chemical reaction includes such things as temperature, the concentration, the use of a catalyst, the pressure if the system is gaseous, or even everyone's favorite, the impact and influence of surface area on the rate of a chemical reaction. A diagram commonly associated with the study of rates of reaction is a progress of reaction diagram. A progress of reaction diagram includes on it the change from where we start to finish, which is our change in enthalpy of a reaction, but it also includes a hump that connects the reactants to the products. The size of this hump is something that's known as the energy of activation. The energy of activation represents the minimum amount of energy required for particles of A and B to collide with each other so that the collision of the A and the B is sufficient, has a sufficient amount of energy that bonds get broken and new bonds get formed, converting the A and B from reactant into product. If a collision only has, say, this much energy, it's insufficient to cause A and B to convert to product. At the peak of the energy of activation hump, when A and B collide, they create something known as the activated complex. The activated complex is a transition period where the molecules are no longer A and B, but they're not completely C and D just yet. It's as though they're teetering on top of the activation energy hump, where they could snap back to be reactant or could proceed over the hump and turn into products, C and D molecules. Another type of graph commonly used in rates of reaction is a kinetic energy distribution curve. This is essentially a curve that represents what the kinetic energies are, the average kinetic energy of the reacting particles. Kinetic energy distribution curves can be used in conjunction with a progress of reaction diagram. For example, going back to our progress of reaction diagram, let's say that the A and B reactant particles are at an energy level of 20, and the peak of the activation energy hump is at 60 units of energy. That would indicate that the height of our hump here is 40 units of energy, which indicates that the A and B have to collide with a minimum of 40 units of kinetic energy for the collision to possibly be successful and lead to product. Now on our kinetic energy distribution curve, we can put in a label here. We now know at 40 units of kinetic energy, this would be our cutoff where we can place our energy of activation line. What this tells us is that all particles that are beyond this amount of energy, anything that has 40 or more units of energy, these represent the particles that it's possible to get over the activation energy hump and turn into product. In this case, the majority of the particles lack sufficient energy to get over the activation energy hump, and so in this case it would represent a reaction that may probably be going relatively slow. In the first part of our lab, we're going to take a look at how concentration influences the rate of a reaction. Concentration has no effect whatsoever on the progress of reaction diagram. Changing the concentration does not change the initial energy the particles have. does not change the energy the particles have when they finish, and does not change the height of the activation energy hump. Concentration merely changes how many particles are available to collide with each other. Typically, an increase in concentration allows for particles to collide more frequently, so the odds of having a collision that's successful becomes greater and can cause the reaction to go faster. This can be reflected on the kinetic energy distribution curve. An increase in concentration merely means we have an increase of all the particles, so there's going to be more A's and B's at all the different levels of energy. So what we'll see is our kinetic energy distribution curve would move up. Since our vertical axis represents the number of particles, an increase in concentration would be reflected by the distribution curve moving upward. What this now does is the number of particles over here that are now beyond the activation energy, which have the minimum amount of energy to react, is now a greater number of particles, and the reaction can proceed at a greater rate. Let's take a look at a simple representation of a reaction, merely just X turning into Y for our reaction. Now let's say we can measure the concentration of both X and Y and plot this data. Our vertical axis is concentration. Our horizontal axis is going to be time. Initially, there's a large amount of X. Now as the reaction proceeds, the amount of X is going to diminish. What we'll notice is then that the concentration of X is going to drop as the reaction proceeds. And we would see something that would look like this as we chart concentration of X dropping as time goes by. Meanwhile, initially the concentration of chemical Y started out at 0. As the reaction proceeds, the amount of Y is increasing, given that X and Y are reacting in a 1-to-1 ratio. As we go down by 1x, the amount of Y will go up by 1. So the curve for Y would look like the X curve, except it would be a flipped or mirror image of that curve. Now if we consider for a moment that the rate of a chemical reaction is the change in concentration over the change in time, and that when we make a plot, the slope on our graph is the rise over run, we can see on our graph here that the concentration is our rise and the time is our run. Consequently, our slope on this plot will give us the rate of a chemical reaction, and that our rise is the concentration, our run is the change in time, and rise over run will give us the slope on our plot. Consequently, our slope on this plot will represent the rate of the chemical reaction. Now, when we refer to rate, there's also different types of rates. We have both average rate and also instantaneous rate. Our average rate, for example, for chemical X, would be our total change in concentration divided by the total amount of time for that concentration change to take place. So again, if we look at our average rate, that's going to be the change, our total change in concentration divided by the total time interval for that change in concentration to take place. Instantaneous rate, on the other hand, is finding the rate at a specific moment in time using a tangent line. For example, if we want to know the rate right at this moment in time, we'd have to draw a tangent line at our curve and then do our rise over our run for the tangent line to get our rate. If we wanted to know the rate over at this point in time, we'd do another tangent line, and again, if we do rise over run, we'd get our rate at that point in time. So a tangent line anywhere on one of our curves doing rise over run on this tangent line would give us our rate right at that exact moment in time. That would be our instantaneous rate rather than our average rate. So again, our instantaneous rate is represented by finding a tangent line on our graph and taking the slope of that line at a specific point in time, and that would give us the rate of the reaction right at this moment. Whereas average would be what the entire change in concentration is over the entire change in time, would give us the average rate of reaction for that particular chemical change. Another aspect of the rate of a chemical reaction is that rate is, by convention, it's always going to be expressed as a positive number. Now, if we take a look at our graphs here, we'll notice that for the formation of product, our slope is always going to be positive, and that it's sloping in the upward direction. So our rate of the chemical reaction in terms of the product will always be a positive, where this would be the change in y over our change in time. However, if we look at the disappearance of the reactant, for the disappearance of the reactant, we can see that our tangent lines and our slope is going to give us a negative quantity. Consequently, to make the rate be expressed as a positive number, in terms of a reactant, this would be the negative of the change in x over our change in time, would give us the rate of the reaction in terms of our reactant for this particular reaction.